Hello and welcome to Embedded Internals. This is third episode of our series, Execution Awareness series. Episode we are going to check the compilation stages. GCC compilations run in 4-stage pipelines. That is preprocessor, compiler, assembler, and linker. Today I will show you the same program which we have created in our first episode. Then we will check. So we have this program hello world.c. This is a very simple program to print a statement. Statement is hello world, welcome to embedded internals on the output screen. Output screen, that is terminal in this case. So to compile this program, we have a standard command GCC and the file name. So our file name is hello world.c. When you run this, you get an a.out file, that is assembler output file. This is a ELF. When you check a.out, you will see this is a ELF file. ELF is a structured binary file which has all the information that it can be directly loaded by the loader into the RAM to run our program. So what is this ELF file? What this ELF file contain and how this ELF file get generated by one simple command, that is GCC. What is happening behind the scene? When you give hello.c, first step it goes to preprocessor. So first you need to check what's the input and what's the output. Input to the preprocessor is .c file and output to it is .i file, and in between we have preprocessor. Question arises, what exactly happening at the preprocessor level? Which tool is being used here and how we can see that what is exactly is happening at this stage. So we can say that .c is our human level code, okay, and .i is preprocessed file, okay. At the preprocessor level you are giving .c file, and after the preprocessing using the tool CPP tool, which expands hash includes, which replaces hash defines and the comments in the code, get one file which is hello world.i. So we can say at this stage text manipulation is happening, okay. So what kind of error you get at this stage? If there is any macro issue, because macros are being replaced and expanded, so if there is any macro issue inside your code, like anything defined as hash defined, hash square, or any macro you are using in the code, let's check this inside our code. What is actually happening at this? I'm giving the command gcc -e hello world.c. .c is the input to it. Although the output got printed at the screen itself, but we need a particular file. So I got that all these output into this particular file .i. So when you see, this file is 21361 byte and it contains 824 lines. This is such a huge file as compared to, so this is stdio.h, libraries, everything get included inside it. So it's a very big file. Whatever the content of this stdio.h, that got included here. Checked, all the text manipulation is happening at this stage, at the preprocessor stage, okay. It's contain the whole data. When you see the size of .c is 290, whereas size of .i is 21361. So this is a large file compared to our C. After the preprocessor stage, let's move to our second stage, compiler layer. We are using CC1 tool. So tool which is being used is CC1. Now what the CC1 tool check? So any kind of syntax error you get in your code is from compiler stage. So it's check the syntax of code. Perform C to assembly language as .s output we are getting. So it converts our code from C to assembly language, which is more close to machine as compared to our C program. It also performs all the optimization. So after the optimization, code size will be reduced here as compared to .i file. In the compiler stage, we are giving .i as input file, and at the output we are getting .s, which is the assembly code. Tool which we are using at the compiler stage is cc1 tool. What is happening at compiler stage is it check the syntax. It convert the C programming language into the assembly code which is very close to the machine language. So we can say that at this stage our code get converted, a text file get converted into CPU instructions. Okay, and at this level code optimization also happens. Any kind of error which we get from the compiler is termed as syntax error. So to check what is actually happening at the compiler stage, we can use GCC -s and our file name, that is hello.c or helloworld.c. Okay. This is the command to check at the compiler level. Okay. So we can say now at this stage our code get converted into readable machine logic. Let me show you the same at our terminal. What command I have explained, that is gcc-s. So gcc-s hello world.c and output file will be in .s. Now we get one file, that is .s. Now see the size got reduced, so optimization has been done. Okay, so as compared to .i. Now let me show you what is in that .s file. What should be, it is an assembly code. Let's see, this is a assembly code file. Dot file, that is hello world.c. This is a read only data. In the ELF section it will go into .ro. This is text file. What string we are printing? Hello world, welcome to embedded internal. This is a string, so dot string from dot text file, and from which function? That is main function, which is a global function type. Main is a function type. Similarly, now the main is being expanded. At the main, which function call is being used? Printf inside put. So puts at the rate plt is called. Particular move from one register, di register to ax register, then ax register to ip register, like this. This is the assembly level code. In the ELF, where we can, in which section we can see, that section has been mentioned here. And all the data, whatever is required by this file, is now converted into CPU instruction. Now this program will get easily understood by the CPU. So this is the second stage of our compilation. After pre-processing, compiler stage. At the compiler stage, we can see this is where our logic becomes CPU instructions. Okay. Now let's move to third stage. So now the input file will be .s and our third stage is assembler, and we get output as .o, which is object file. Tool which is being used as at this level is AS. So we need to check what is exactly happening at this stage. So at this stage our assembly code is being converted into machine code. Assembly code logic or the code is being converted into machine code, which is now further more closer to machine. Reallocatable object files. We can say that now our machine code has been generated. This stage, one thing which is not happening is linking. We will see at that. So this two the task is doing. How we can check? So what kind of error we get at this stage? anything which is which is related to missing symbols, whether the particular thing is defined or not defined, that kind of error we get it from this level. So to command to check is gcc hyphen c, sorry, gcc hyphen c hello dot get the object file at this stage. So we can say .o file will contain machine instruction, but it's still not complete program, because particular definitions like printf, scanf or any particular definitions which I've used is still missing from that code, as library has not been linked. Let me show you that same from the terminal shell. gcc hyphen c hello world dot c, and the output file which we get is hello world dot o. Okay, hopefully we get the output dot o. Now let me show you if this is machine instruction, so mostly not readable. You can see some commands which is input bss data segments, this library, but that is not readable by programmer. Let me show you what is inside this. So we see at the .o level our output file is of machine code. Now the final level or the fourth level is linking level. Our input file is .o, it goes through a linker, and the output file which we get is a.out or anything which is assembler output, or elf file a.out. It is assembler output, which we see elf file, which is a structured binary format which can be directly loaded by the loader. Now, so what is happening at this stage? At this stage, we actually get the complete program. So first thing, let me tell you that is which tool is being used. At this stage, we are using LD tool, linker tool. Okay, what this does, it does 4 major tasks. First is combine all object files. Second is it resolved the symbols like printf symbol, scanf symbol or any functions which is missing at the object at the assembler language get resolved at this stage. So it resolved symbols. Third thing it do is it links the libraries. Links library. Which library? In this case we have glibc library. And fourth thing we all already have seen is to produce elf file, executable and linkable diff format file. At this level, fourth level, we can say that complete readable code, real code is now we have in the elf file. So elf file is a structured binary data which can be directly loaded by the loader inside the RAM to generate the corresponding output. You write gcc, command is same, gcc hello world.c -o hello world as an output file. The now hello world will be your elf file. Let me show you file hello world, which is an elf file. You will get this file. Obviously you will not able to read this file, we cannot do directly vim. So we can say that linker connects our code to the real world, that is by linking the libraries here. Error which we get at this stage is called linking error, which is directly related to missing libraries, like when you are using some maths functionality or you didn't added math.h, you will get the linking error. Or you are using some threads in the code and you have not linked to pthread library or something hyphen lp, so these kind of error you will get so we have to link at this layer, otherwise we will get our linking errors. The linking level, we have two different type of libraries: static linking, library linking, that is static linking, and dynamic linking. In the static linking, all code is embedded inside the binary itself. So this makes the binary size bigger. But it has one benefit, that is it doesn't have any runtime dependencies. It we can say that it is a self-contained binary. Whereas at the dynamic linking, we link the required functionality at the runtime. This makes the binary smaller and flexible, but it has some architecture dependency as well. So these are two different type of linking. Let me show you how the size get increased in case of static, whereas same doesn't happen in case of uh, dynamic linking. So to create a static linking file, you can use one statement hyphen static hello world.c. Let me create a file static. Okay, is elf. Now see the size of static. This is such a large size, whereas this is created by dynamic. See, size is very small. So this happens at this is the difference of linking. So instead, mostly nowadays we do the dynamic linking only because size matters most in the operating system. So this is the difference of static and dynamic linking, which this linking is happening at the linker level itself. Okay. The compilation is a translation pipeline, not just a single step, which we have seen at like. I hope everyone is clear at this level. What is happening? What are the different compilation stages and what is happening at each stage? In the next episode, we are going to cover what is inside ELF executable. Stay tuned for same. Thank you.